Welcome to the lecture 20 of Symmetry, Structure, and Tensor Properties Materials. Here we're going to talk about P4, our next group. As we've been doing, we started with the primitive lattices as opposed to the centered, and we've added in the last lecture 1, which is of course more or less just an identity, but to show that it's complete primitive we call it P1 because we're just adding this 1, basically no symmetry elements to the primitive lattice. And then we showed how if we look at the next element, the next point group that we wanted to add, which is twofold axes, that point group creates a new combination theorem. And now we can use that combination theorem going forward and make our life easier, for example, in P4. Now the reason, to give you some method to the madness, I want to make sure that you understand, okay, we've already added the twofold axis to primitive axis. So you say, oh, well, why are we doing P4 next? And the answer is, well, there is nowhere else to go. I'm going to keep on increasing the size of the point group that I'm adding. Because remember, as I increase from twofold to fourfold to sixfold, all I'm doing is adding more angles, more group members, and we'll just see, what happens, as we add these, higher symmetry point groups to the primitive lattice. So it makes sense. Now you say, well, I skipped over 3, and that's because 3 is a little bit more complicated. And so we're going to come back to that in the next lecture. But right now, we're all lined up based on our twofold axis. We're really set up for just doing P4. So let's go ahead and knock off P4, where we just add now a fourfold axis to the twofold axis. What I'm showing you here again is to make sure that you see that our graphical work is still, related to this point group theorem, group theory. So P4 point group capitalized. This should be actually a small p because we're dealing with 2D right now. So the P4, actually there shouldn't be anything there at all. I'm looking at just a point group, the fourfold point group. So sorry about that. So this is the fourfold rotation point group. And what you see here is, recall that we always have the identity element, the smallest rotation, pi over 2, which is 90 degrees. Then, of course, I can have 180, and I can have 270, and then when I go all the way around, I'm back to 1, right? So it shows me the 4 elements of this rotational point group. Now, because we've already developed this combination theorem in the last lecture, as we put in a rotation into the lattice, it's going to show us where these other rotations are, right? So now before doing that, notice that a pi is part of any fourfold axis, any fourfold point group that we throw in there, right? Now we've already done that one, right? So we kind of already can identify then on inspection where we're going to introduce new elements. So let's do that right now. Let's say, okay, if I can draw a square, and at these major lattice points, I'm going to put in the fourfold symmetry, actually, like I did the other time. Let's choose a different color. Each lattice point has this fourfold axis inserted, and we don't have to repeat the group element of A over pi because we've already done that one. And of course, what that's done is it says, hey, the translation vectors that we have here, and so on, they're going to be bisected, remember, with the twofold axis, because the twofold axis is in here. So inside this guy, look at, see, we got the 4 elements. There's an A pi. There's an A pi here. So that means that just by inspection, I can put in this one, this one, this one, and this one. Also, it says, well, if I've got two two-fold axes here, I can put in that one, right? So already, I see these extra symmetry elements have to be, part of the group. So again, we already know they're part of the group. It's A pi, but the question is, when I know that they're in this fourfold ones, does it show me spatially where the other group members are? And my theorem does, tell me that. I don't have to redo this because we did that back in the P2, and that's of course why P4 derivation is following the P2 group, because we can just insert these now by inspection using this solve from last time. But of course you know what's coming, which is there's 2 new angles that we haven't looked at yet that are going to be existing on these fourfold axes, which are the pi over 2, right? So what we want to do is use our theorem to say, okay, fine, are there any extra symmetry elements that we haven't seen before, right? And so let's go through that now. Where is B pi over 2? It's going to be at and remember that's at the perpendicular to T over 2, right? So let's look at one of those. Let's look at this bottom one because it's going to be the easiest. If I look at this translation vector, remember the bisector is here. So let's draw the bisector. And if I solve this, right, look at the cotangent pi over 4. Remember, this is the cosine over sine, and you end up with x equals t over 2. Right, so unlike the a over pi case where x equals 0, this equals t over 2. So what that means is in either direction, because there's a pi over 2, 3 pi over 2, etc. All it does is flip sign. You're going to have half of this. Now we know because it's a fourfold axis that half, this t over 2, is also t over 2 up here. And so it brings us right to here. So what it tells us is that the new symmetry element of a pi over 2 angle is not superimposed only on just these, but actually there's a fourfold axis in the middle. Okay? And again, I should draw this a different color because remember that's a separate and distinct fourfold axis from the other two. Now the way we're going to see that is the same way we always do it. Let's draw our motifs, which now is a little bit more painstaking because as the symmetry increases, the number of things I have to draw goes up. But let's see if I can do it, at least a little bit, to give you an idea of what's going on. Right, and we're going to have this at each place. I have to draw them in to show you the other symmetry elements. So we'll get a little pixelated, but I think you'll be able to see what's going on. Okay, oops, ignore that little red line. So I think you can see now how, again, whether we saw them by inspection or not, that these symmetry elements rotate around. So for example, this guy here should be connected to this guy, for example. And this one here, when I rotate it around, ends up being connected to this guy, right? You can see that. So those are perfectly fine. Now, if you look carefully for the fourfold axis, which is why I really drew this, you can see that this guy is created from this lopsided so there's a lopsided square here which relates these elements to each other, right? Actually, it should be this one here, I think. But you get the point, which is that there's a fourfold symmetry about this central one. That's the green. And again, it's induced by the fact that if I put fourfold symmetric motif, point group, if you will, around each one of these lattice points, it automatically means that there's a twofold axis here, which I talked about. There's one here, one here, one here, and that fourfold one, is automatically there as well. And again, they're independent. The blue box is different from the green and blue one here, and the magenta are twofold axes. And of course, they're similar, right? Because each one of these is showing some rotation about these elements, so they have the same environment. Each one of the magenta ones does. This one is, as we found out, not a true different magenta because it's actually a green, and it has an 8 pi in it, but it's actually a full fourfold symmetric group. And there you have then P4.